before we go on to the ASIC material, let's go back to this block diagram of the one-layer engine. This, the Microsoft design and the UCLA design are both optimized for forward propagation, for classification. And we saw that for learning, you have to go backwards, right? You have to do back propagation. How would this block diagram change if you wanted to use it for back propagation? First thing that has to change. What direction? Come here, show me. Come here. Come here. Come here. Show me. Come on, come on. You open your mouth. You have to show me. Come here. Come here. Come here. Come here. Point. Well, so the weight buffer has to change first, right? Because you're not just reading them, right? You're also writing them, okay? So and you're right that the weights not only go in from the DRAM, they also, you have to write them back out, right? On top of that, the network on chip is going to have to change because you have more connections now because you're writing to this as well as this. Okay? Okay, thank you. So, in fact, using this for back propagation, requires significant changes, and I'm not sure whether a back propagation version of this would fit on the same FPGA. My guess is it might not. Okay, so back propagation does require more resources. It requires a lot more memory and a fair amount more interconnect. Okay. Okay, let's talk about ASICs. Okay, we're not going to talk about all of ASIC design, but I want to talk about some topics of hardware design that are particularly relevant to things you might want to do for neural networks. Okay, and we'll move from fairly low-level stuff up through more system architecture. We'll start off with power consumption and low voltage logic to reduce power consumption. We'll talk a little bit about memory modeling. We've seen that memory is very important. We'll talk a little bit about networks, and we'll talk a little bit about custom accelerators. Okay? So, good news about CMOS is that you can actually run it at a wide range of power supply voltages, right? This isn't true for all logic families. Not many logic families are as flexible as CMOS in the range of power supply voltages they're tolerated, right? The lower, so what happens when you reduce the power supply voltage to a CMOS gate? What happens to its power consumption? Only two choices, up or down. Power consumption is going to go down as you reduce the power supply voltage, right? What about the delay? Delay goes up, right? So, very, very simplified models. The delay increases linearly with power supply as the power supply voltage decreases. Okay? And that's because the effective resistance is a function of the power supply voltage. Okay? So speed power product is a common metric for a lot of logic families. It's particularly, so we use it to compare different logic families, but within CMOS we can say, well, we're operating at this power point, so that gives us this amount of delay. Now all that is dynamic power that depends upon the gate switching, right? Modern CMOS also burns power even when it's not doing anything. Okay, most of that comes from leakage current, and there's a whole bunch of leakage mechanisms. Okay, but basically the only way to stop leakage is to take off the power supply, which you can do at different levels of granularity, right? But you can use transistors, which are usually called sleep transistors, to remove power supply from a block of logic. Okay, so this nice relationship between delay and power leads us to a power management strategy that we call dynamic voltage and frequency scaling. Okay, if we know how much performance we need, right? That tells us, in some way or another, it tells us the delay we need through the logic, right? And from there we can determine what power supply voltage we need in order to hit that delay level. The other way to look at it is, if we have a maximum power consumption we can tolerate, and we saw that thermal says there may in fact be just an upper limit on the amount of power we can burn. Right? From there we can say, well, that means we're going to run this fast. Okay? So modern processors are constantly jockeying the power supply voltage and the clock frequency in order to hit performance and power goals. Right? There's all sorts of fancy techniques you can do to determine where you should be on the power scale and on the delay scale, but it all boils down to these very simple relationships for power and delay. Okay? Now my student Seon Kim looked at a more aggressive approach, which is actually operating below the threshold voltage of the transistors. Okay? So standard DBFS assumes that, you know, the logic levels are above the threshold, so the transistor's on. Right? If we're below the threshold voltage, the transistor becomes weaker exponentially, but it's not entirely off. Right? So we would expect that if we go operate at a very low power supply voltage below the threshold, that the logic would be slow, right? And in fact, that's the case. Okay, so this plot shows you for a number of different, this is for an adder, and so this shows you for different inputs the spread of delays, right? The delay is going to depend upon the input value you give the adder, right? But it also depends on the power supply voltage. So green is 1.4 volts, yellow is 1.6 volts, red is 1.8 volts, right? So at the highest power supply voltage, you have the lowest sort of average delay, right? Each of these is a bell curve with a different center. The bell curve for 1.6 volts is around here, and the bell curve for 1.4 are like around here. Okay? So the logic doesn't stop working. It doesn't just stop, but there is a penalty for this, right? What do you think the penalty is? The penalty is errors. Okay, so this plot shows you, this is voltage from high to low, right? this is delay, this is the carry out, and this is the overall sum. So you can see that the carry out and the sum increase, super linearly as the power supply voltage goes down, right? So if you turn down the clock frequency, along that same curve, if you wait long enough, then you'll get the right answer, right? But you may not be willing to turn it all the way down, right? Because remember that the delay depends upon the input values you get, right? So as we decrease the power supply voltage, not only does the center of this bell curve move this way to longer delay, but it spreads out. Okay? So we see more variation as a function of the input values at low power supply voltage. So to make sure we capture all of these, you see there's one value all the way out here, right? We'd have to wait a very long time. So the option is to occasionally not wait long enough and get the wrong answer. Okay, so the question is, what's the error model for that? And Sion came up with very interesting models. So previous work had come up with what turns out to be a pessimistic model for delay. And Sion's model is more accurate because his model is not simply combinational, it's sequential. Okay, so the previous model just said the delay is a function, the error rate is a function of what input you have, right? But for something like an adder, it depends not only on the current inputs, but the previous inputs. Okay? So the delay depends upon the transitions in the carry chain because that's going to limit the delay of the adder, right? So here is we're adding two vectors of all ones. We have a carry out of every bit, right? We expect that to be the reverse case. In this case, we're adding all ones to plus 1, you get a carry out of all these bits. In this case, we are getting, we're adding 1, 0, 1, 0, 1 to 0, 1, 0, 1, 0. In fact, there's no carries anywhere. That should be the best case, right? Okay. The delay depends on the inputs, clearly, and it depends upon the state of the carry chain. Okay? Okay, let me go back here for a minute. Okay? So, we know that CMOS is a capacitive-based logic, right? Every logic gate has capacitance as the inputs, and that capacitance stores, at least for a short amount of time, the last inputs to the logic gate, right? So, if we did this arithmetic operation here, we had this carry chain, right? We had a carry on every bit, right? And then the next operation was this one. How many bits of the carry chain would change? From here to here. None, right? So there's not a lot of delay on the carry chain, right? When we go from the second example to the third example, how many bits of the carry chain change? All of them, right? Okay. So that's going to take longer. Okay, so the delay through the carry chain depends not just on the input values, but also on where the last set of inputs left the carry chain. Okay, and so you can do some experiments, you can do some statistical analysis. It turns out that that means that the average delay is less than you would think if you don't take into account the sequential dependency. Okay, so this plot compares the static that doesn't look at the previous values to Sion's model, which does. These are for different arithmetic algorithms: triple carry, Kaji Stone, and array multiplier. And you can see that the static delay estimate is much more pessimistic, much bigger. Okay? So this gives us some hope about how useful this technique could be. Okay. Now keep in mind, Sion did this work originally for image compression, slightly different domain, but you know, we're still doing a lot of arithmetic here. Okay, so basically you end up with a you need state in your delay model. Okay, you need to know that it's the state of carryout bits. But you can build this stateful model and use it to model the overall delay of the app. So, as I said, Sion used this for image quality. And for image compression, you're going to do a lot of discrete cosine transform, which is going to have a lot of multiplies and adds in it, and so forth. And basically, you looked at how to design a DCT unit that would be, you know, hardware efficient and low power, and came up with 3 different cases where you have to worry. One is where the sign of the 2 inputs are different and the magnitude of the values is small. Another case is different signs and both the inputs are large and similar magnitude. Okay. Third case is same sign and a big difference in magnitude, right? Which is this sort of -1 + 1 kind of case. Right. So those cases, in the case of, well, you have to look at the application and say how frequent are those. In the case of DCT, they're not extremely frequent. If you were going to use this for neural networks, you'd want to look at the statistics of the values you're using and see how common they are. Okay. It turns out there is a interesting problem with this, though. That in the case of image compression, that having errors in the DCT operations and the multiplies in the DCT is not such a good idea. Why do you think that's the case? So think about JPEG, using the DCT to do compression. How do you use the DCT for compression in JPEG? So JPEG computes the DCT and then it sets some values to 0, right, in the DCT, which loses some information, but it makes it easier to compress that matrix, right? Because now you have more zeros, it's easier to compress. What if you have more errors in your arithmetic? Then you're going to have fewer zeros in that DCT output, which means it's going to be harder to compress the output of the DCT. right? So you're going to save energy in the DCT, but then you're going to lose it because you're going to be writing more stuff out to memory. It turns out there's another technique in this domain, basically truncating. And my colleague Shaibal Mukhbahedi actually came up with a memory architecture that allows you to truncate efficiently, right? But consider applying this to the neural network domain. You've got a somewhat similar situation in which you're doing multiplications for the convolutions and then you're doing a nonlinear operator. Okay? If you introduce errors into the nonlinear, into the multiplication, how does that affect the results of the nonlinear operation? Are you going to get more, are the nonlinearities going to amplify the problems, or are they going to tamp them down? Quite frankly, I don't think that, I don't know of anybody who has the results to say whether this is a good idea or a bad idea in the neural network domain. But given how important power consumption is for neural networks and for training in particular, somebody should probably look at that problem. Okay, so that's my observations on power consumption and logic level. Let's think about memory for just a minute. You know, a simple memory is a two-dimensional array, right? We can divide up the address into row and column. We can select out a row and then sub-select the columns we're interested in that, right? Okay. So we have wires for the rows, we have wires for the columns, we have pre-charged circuits and so forth. The people have looked at how to model the area and the delay of memories based on this structure, right? So we can compute the total area of the memory array based on the core, right? The row logic, the pre-charge logic on the columns, and then the column decoder logic down here. Okay? So given, we know the size of a 4-cell row, pre-charge and column, we know the number of rows, number of columns, we can figure out the area. Right? This also tells us that there is overhead, right? So, if we have very small memories, most of the area is going to go into the overhead, right? This is why people normally like really big memories, because the size of the row and column circuitry is small relative to the size of the core, right? That's why you have small, fairly big arrays in CPUs. But in the case of neural networks, we want to operate in parallel, right? So we want a lot of smaller memory blocks. Okay, but if we make memory blocks too small, then it's going to be mostly overhead. Okay? How about energy and delay? There's of course, a static energy component, right? But in the case of energy and delay, we can look at the cost of the row decoder, the core, pre-charge, and also the column. Okay, so once again, we can characterize these cells independently, and then the delay depends, things like the bit line delay depend upon the size of the memory. The row delay, for instance, does not. Okay. We've seen that we get more parallelism by having multi-port memories. We saw that FPGAs have 2 ports. Okay, so in fact, for SRAM, the delay of the SRAM is slightly more than linear in the size, in the number of ports. And the delay of the memory is also, and as this plot shows, a function of the memory size. So the x-axis is the size of the memory, and the different lines are different number of ports, from 1 port all the way up to 8 ports. Okay, so you can see that the slope of the line gets steeper as we go to more and more ports. Okay? So more ports may sound good so that we can read and write more values in parallel, but it also means that each memory is going to be slower. Okay? That's another basic trade-off we have to make when we're deciding the granularities of the memory. So if we're designing an ASIC, we need to decide how many blocks we need, how many ports each block needs. Okay? And what's the relationship between the number of ports and the number of blocks we need? What if we have only 1 port on each block? Well, if we have only 1 port in each block, we can only do one read or write at a time, right? So if we want more parallelism, we would need more blocks. Okay? Which means more overhead, more area overhead per block, for example, right? If we have more ports, that means that we need fewer blocks, but we also make sort of the global routing model perhaps a little more complicated. And we slow down each operation somewhat because the delay increases with the number of ports. Okay? So, don't have a nice simple formula that says here's where the trade-off is for neural networks. But these are the considerations that you have to keep in mind. Okay. We saw that you need a network in order to connect up these elements, right? If we had entirely fixed connections, the FPGA interconnect would be fine, right? But we can't change the FPGA interconnect on every clock cycle. Right? We need to design a network that can change from cycle to cycle. Okay? And so the first choice we have to make is the topology, or how rich the interconnection is. Right? So the two extremes are bus and crossbar. Okay? A bus is a single shared connection. It may be n bits wide, but each bit, right, is shared between all the inputs and all the outputs. Okay? So that means if we need to do n transfers, it's going to take n cycles. Right? Crossbar is the exact opposite. It connects up. It allows you to do arbitrary combinations of the inputs and outputs. Okay. How do you make a crossbar? Well, here, just a second. There's a bus, right? This may be n bits wide, but it's a shared connection between all these blocks here, right? So, we want to transfer from here to here and from here to here. That's going to take 2 bus operations, right? And if the data is wider than the bus, each of those operations may take several clock cycles. Or if it's a very long bus, it may take several clock cycles. So it's easy to design, easy to program, but we have contention. right? If we have two things that want to do transfers at the same time, we can only do one at a time, right? And we know that in the case of neural networks, we have a lot of things a lot of transfers we want to do in parallel, and we know exactly what those transfers are for the most part. And this is one case where this highlights the difference between forward propagation and back propagation, right? So in the case of forward propagation, we're going through a very fixed pattern of interconnects. In the case of back propagation, some of them are, algorithms are extremely regular. In some cases, we may not want to do all the transfers. We may not want to adjust all the weights at any given time. Okay, so bus is probably not the best choice for neural network. We saw that the UCLA group used a crossbar for their network. How do you build this crossbar? Okay, right. So you've got horizontal wires, you've got vertical wires, and you can use a transistor or something a little fancier than that to make programmable connections, right? So let's put all the inputs on the top here and all the outputs on the right here, okay? So if I want to send the leftmost input to the topmost output, I would turn on this cascade right here, right? If I want to send the leftmost input to the second output, I would turn on the second cascade. Right? But as long as there are no interference between where the inputs where the outputs want to go, I can do any combination, right? So I can send this input to here. I can send this the second input to the third output. I can send the third input to the second output. Fourth input to the fourth output. Any other combination. I can also do multicast. I can take this input, the leftmost input, and send it to two outputs. Right? So it's very rich. It costs you n squared, right? You have inputs and n outputs. The area is n squared. Good news is at least those cascades are small. Delay also is significant, but for the size of crossbar we're talking about on a neural network, probably not that bad. We can probably afford to do that. Right. There are versions of the crossbar that have somewhat less connectivity, that don't allow you to do all the multicasting, but for point-to-point have the same richness as the crossbar. Another way to reduce the cost of crossbar is something that's done in networks a lot, which is to add buffers, either at the inputs or internally. Allows you to reduce the interconnect network, but it also means that you have to schedule the transfers a little more. Okay? In the case of the crossbar, you set it up and you can just pump data through however you want. In the case of when you have these buffers in there, you have to decide, okay, this input wants to go to the output, but this other queue is using it right now, so he's going to have to wait. Okay? You can look at mesh architectures, right, which could be two-dimensional or higher dimensional. Once again, some value may have to wait because another value wants to use a particular link, but these give you a nice flexibility between richness and cost. Okay? Are also, fairly easy to program, well understood. So, actually, I think in the case of neural networks, the application specific probably, well, application specific would make sense if you could unroll the network and have a different stage, different network topology for each stage, right? In the architectures we saw in the FPGA section where we're using the same network for every layer, that network has to be fairly general, has to be able to do all the combinations. If you're doing a fully unrolled neural network where each layer has different interconnect, you could build interconnect that was tuned for each layer. Okay. If you have a full crossbar, you don't need to worry about routing. These other types of networks do require routing. Okay. So you need logic inside the network that can look at an address and decide where to send packets. Okay? And there's a whole bunch of schemes on how you do this. For something like a mesh network, you would have a flow control scheme that would basically decide who gets the link next, who gets a particular connection from one point to the next point next, and where you're going to store something inside the network while it waits to get transmitted along the next step. Okay? So if you're doing a neural network that only is doing forward propagation, this type of network might be a little more, might be too much, unnecessary. If you're doing both forward and back propagation, then a more sophisticated network might make more sense. Okay. So there's a whole bunch of work on networks on chips that will look at the different routing schemes, width of the network, all sorts of things. Okay. Okay, so there has been some work on convolutional neural network architectures that are custom. Okay. And this paper that came out in the journal version, at least, came out in 2016, is one of the more ambitious examples of that. This paper, this block diagram is from their paper, shows you the basic structure. So a lot of the work they did went into the memory design. As we've seen, memory design is very, very important. And they worried a lot about how to reuse, which relates back to the loop organization that we talked about. They look at it as a reuse issue, but you can also cast it as a loop optimization problem. Right? So you have a window over the inputs that you're sliding through this larger set of inputs. Right? So you want to put things in memory in the right way so that you can efficiently move that window and avoid multiple fetches. And you want to be able to store the outputs in a way that you can use it as the inputs for the next operation as well. Okay? So in this block diagram, here's memory interface, local buffer, right? So they're not storing that entire block at once. They're doing a set of operations here. There's some pipelining in there. And then those go into an output buffer that eventually goes either to main memory or to the next layer. Okay? So they identify two types of weights. There are some weights that are shared right? So that different synapses will use the same weights, and there are some sets of weights that are not shared, that are not reused. Okay, so this figure comes from their paper, and it shows how they reorganize the loops a little bit in order to map it onto their hardware structure. Okay, so it's a little hard to see. But first off, they actually have two loop bodies, one for shared kernels and one for private kernels here. In this case, this is with average pooling that's using the average operation, pooling that's using the max over here. But if you look at this set of loops here, there is well, there's 1, 2, 3 layers here. This is an initialization, and then there's 4 levels of loop here. Okay, that's sort of the main body of the loop. So they have. Let me make sure that I'm got this in the right. Pointing out the right thing. Okay, so this loop corresponds to this loop here. This corresponds to this loop here. This corresponds to this. And so the end loop is basically unrolled into parallel hardware units. Okay? And then yeah, I believe that some of these loops are doing initialization here and set up for the other loops. Okay? So this illustrates how they're basically sort of unrolling the computation not in software but in hardware. Okay? Because they have parallel function units. So they went into a lot of effort in this design. They actually synthesized it. I don't remember if they fabbed it or not, but they definitely synthesized it on a 65 nanometer process, which is not particularly new, but it is a real design. Their synapse. So they didn't do a heck of a lot of numerical optimization in this thing. For instance, they used the sigmoid operation, the 1 over 1 plus e to the minus x, like your nonlinear operation here. So even without a lot of numerical optimization, this shows the energy, size, and delay for different sizes of units here. Right? So you can see that the area, of course, goes up. I don't know why. Well, 64 by 8, 32 by. Yeah, so this is sort of not, this dimension is not exactly linear, right? This is 32 by 32, that's 32 by 4, that's 128 by 16. So the area gets bigger for the more parallel as you would expect. The critical path delay doesn't go up that much, right? And the power consumption is probably a little more than linear, right? As you do more in parallel, it's probably a little more than linear, but it's not bad. So, you know, and there's no direct comparison. It's not easy to compare this in any meaningful way to like the GPUs or the FPGAs, right? What's the exact benefit you're going to get by doing a custom processor rather than an FPGA? Hard to say, but you got to believe it's going to be there, right? But so I think they did enough to demonstrate that there is a significant benefit from going to the effort of designing an ASIC. But I also think that this is doing a full custom design is a big problem, and there are plenty of optimizations that they didn't consider that could give you more benefits in the long run. And I think that one of the more interesting questions is, if you did more optimized numerics, right, and really squeeze the size of the numerical operators, would that give you much real benefit in the amount of memory, the amount of area you had for memory? I don't know. It would definitely make a difference in power consumption. Would it make that much difference in the number of weights you could store on chip, for example? I just don't know the answer. Okay. So, any other questions about the ASIC approach? Yeah. Yeah, like what? Oh boy, I don't remember which process parameters we used, but he did this all with spice simulation. I really don't remember the process parameters we used, but it's something that we can have access to, right? So it's doing all the process. Basically, he generated random inputs, right? And ran a spice simulation to evaluate the delay. Okay. And of course, he looked at the correlation from case to case, right, from one to the next. Any other questions? Yes. Arrows in what mathematics? Where? Error? Oh, because right, the in standard logic design, right, we assume we're going to wait long enough that we're going to wait longer than the worst case delay, right? So that we never have an error, unless there's something else going on, right? That's not what we do here, because as we lower the power supply voltage, the variation in delays increases, right? So if you're operating at a high power supply voltage, the difference between the best case delay and the worst case delay for the adder is smaller. You won't wait for every worst case to be stable. Most of them will be stable, but some of the outliers will not be. That's where the error comes from. It's not random, right? We know the inputs, we know the circuit, we know we're going to get an error in this, but we deal with it by saying it's a random variable. Right? Yes, this is approximate computing. We were doing this 8 years ago. Yes, but it is approximate computing. Yes. So, as I said, we looked at this in the case of DCT. We would have to evaluate what these errors mean in the case of neural networks, and my concern would be the relationship between the multiplications and the nonlinearity. Right, that's right. That's right. But the interesting thing on Sihon's results is that the error rate is much lower than was previously thought because the model is more complicated. Right? It turns out that the worst case doesn't happen as much as people thought, because the worst case depends not just on the inputs, but on the state of the carry chain. Okay? So that's certainly going to hold in the neural network case. How it plays out in the particular functions you're using for the neural network, I don't know. Yeah. Well, that's basically what he did in a bunch of experiments. He ran. He ran. Well, this plot shows the number of faults, right, for different bit widths for these different algorithms, right? So he generated these plots by randomly generating values, running spice, and getting the delay and saying, is the delay bigger than some value we're using for the clock cycle? Right. Yes. So he did it, and this is a big difference in delay. Right? We're talking less. In this case, 4% versus 24%. Right. So the old model was way too pessimistic. Okay. Anything else? Yeah. For CNN, I don't think anybody has really good numbers, right? Because there's so many variables, it's hard to compare. So I don't think anybody has good numbers, but it's got to be significant, right? It's almost certainly worth doing. Let's put it that way. Well, more than 10x, I don't know. I don't want to say something stupid, right? But I'll tell you why I think it's going to be significant, and it goes back to this other plot here. And this is particularly true in the case of training. This one. Right, go back to these plots here. And this is training, but it shows you how many machines you need for how long. Right? And they're saying even in the best case, 1,000 machines for half a day. Right? And given that power consumption, excuse me, let me put my microphone up here where you can hear me. Given that power consumption is one of the largest components of cost of ownership of the data center, right, even a small improvement in power consumption, when you got this many machines running, it's going to make a big difference, right? If you were only going to, right, if you only needed one of these ASICs in an entire data center, it probably wouldn't be worth doing, but that's not the case. You're going to need a lot of them. And the power consumption difference is going to be significant enough that it's almost certainly worth doing. But I really don't want to stick my neck out and give you an exact number. Any other questions? If you're done with questions on this, people want to talk a little bit about neuroscience. I'm not a neuroscientist. You should probably discount everything I say about neuroscience, but we can talk about it for a couple of minutes. Okay? First thing to keep in mind is that there are two reasons to build these electronic neural network machines. And they're very different machines. They're very different reasons, and sometimes people confuse the two. Okay? On the one hand, you can use these machines in order to help you do neuroscience. Right? It's easier to see what's going. It's not that easy to see what's going on in a chip, but it's a lot easier than sticking a probe into a person's head. Right? So we can build these machines as models of what goes on in people and other types of animals. Right? That's an important use. Okay? We can also build these machines to solve industrial problems, to help people shop for clothes, to avoid running over people with your autonomous vehicle. Okay? If you're doing neuroscience, you want to build an architecture that relates to the way the brain works. Right? Because if you build some totally weird architecture, it doesn't tell you anything about the brain. If you're trying to build a collision avoidance system or a shopping system, it doesn't matter whether it works like the brain does or not, as long as it works. Okay? So it's important to keep in mind why you're building these machines, what types of trade-offs make sense for your end use. Okay? So given that, how many of you have taken a course in neuroscience? 0. 1. Okay. So there's two things we can talk about, really. The sort of the neuron itself and then the overall structure, the visual system. That's the part that the brain is a complicated thing. The part I've sort of read a little more about is the visual system. So keep in mind that a neuron is much more complicated than, even a fairly big chunk of logic, right? I know I'm going to mess up my terminology here, but we have a head, we have a bunch of connections feeding into the head. These are the dendrites. And the individual connections are known as synapses. Axon. And at the other end, we have dendrites that go out to the other side of the synapses. Okay? So the synapse is a connection between two neurons. And we can have two types of connections. Exciting or inhibiting. Okay? So one neuron can when it fires, its connection encourages the next neuron to fire. Okay? Or an inhibitory synapse, when the first neuron fires, it discourages the second neuron from firing. Okay? So there's details and difference in how these work, but basically neurons support both models. And as I understand it, most neurons have some of both. There's probably a difference in the richness of one versus the other, but there is some mixing of the two. Okay, so you have and how are signals encoded in the neuron? So let's say we want to encode how hard I'm pressing down on my finger, or how bright the light is at a certain point. How is that encoded?
Frequency of spikes.
Spike frequency, right? So it's a spiking system, and there are artificial neural networks that are spiking models. The neural networks that we talked about here, the convolutional networks, are not spiking models. Okay, so right there, they're different from the way the neuron works. Okay, so we've got pulse trains. Right, each pulse is pretty much the same as every other pulse. The frequency of the pulses encodes intensity. Okay. The dendritic tree, as I understand it, can be modeled pretty well by transmission lines. Right. So basically, the dendrites are adding together pulse trains from various sources. Okay. So you get all these summed up pulse trains coming into the head, and this is where the nonlinear operation occurs, right? It decides when to fire based upon how the rate at which pulses are coming into it. Okay? So for a given rate of pulses, it may fire at some rate, and there's a maximum rate at which the neuron can fire. Right? But it's going to decide how frequently to fire based upon the rate at which pulses are coming in here. Those are going to be transmitted down the axon, which is once again pretty much I think of the transmission line, and then they're distributed out at the other end to synapses that go on to the next neuron. Okay? I believe it's Sir John Eccles' book that is the standard book on neurons. Okay? And the name of the book leaped out of my head. I can't remember, but it's easy to find. It's a book that's 50 years old, but it's still the classic. He figured out how neurons worked by finding a sea slug that had these giant neurons that he could just poke probes into. Okay? So he did pioneering work on how a neuron works. Of course, you have to put a lot of these. So this is much more complicated than even a logic gate. Right? The encoding of data is very, very different. The rate at which this operates is relatively slow. Okay, I forget what the maximum pulse rate is, but it's not particularly fast. Okay. So very different type of operator. Okay. But clearly one in which we can take advantage of parallelism because we can build a lot of these things and we have a lot of synapses. Right? You have thousands and thousands of synapses feeding into each neuron. So we put them together. The best overall book on the visual system that I found is called Vision Science. And it gives you a good overview of some of this, shall we say, structural neurology, as well as sort of higher level models of how the visual system works. And we still don't, I don't understand anything about how the visual system works. I think that vision scientists still don't understand everything about how the visual system works, but for the past half century, we made a lot of progress. So one thing to keep in mind is that visual processing doesn't just happen in the brain, it happens starting in the eye, all the way through the connections back into the visual cortex. Okay. So we talked about lateral inhibition this morning as a way to increase contrast. That's done inside the eye. It's very early processing. Right? But that helps. It's easier to do it inside the retina than it is at later stages. So it's probably a good decision to do it there. There is some amount of processing, I believe, that's done along the pathway from the eyes into the visual cortex. The studies of things like recognizing objects were done in the, I think, mostly in the 60s, perhaps in the early 70s, by taking, I think they were cats, small animals, presenting them with different things at different parts of their visual field, and putting probes into their brain at different positions and also at different depths. Okay? So one of the things they found was that, as I said, that you can map the visual field onto the visual cortex. So you can say this point in the visual space is processed at this point in the brain. And of course there's left and right eyes. Right? So they could tell that by putting something in the visual field at this point of the cat and probe it around until they found where in the brain was active with that stimulus. Okay? Now, how do you think depth plays into this? What does depth mean in visual processing, in the visual cortex? Well, it relates to shape complexity, and I think perhaps motion may play into this also too, right? So how would you recognize a line at a given orientation and at a given position in the visual field, right? So there's a line here. And you've got neurons, you have neurons that represent different points of the retina, right? So if that means, dark, if it's a white line against a dark background, right? That means dark, right? This means light. You can wire up excitation and inhibition such that when the line is oriented this way, right, these neurons are not being, these neurons say that it's dark and these neurons say that it's light. Okay? So now you can unroll that loop right across the entire visual field, right? What's another layer of the loop that you have to unroll? Well, there's orientation first, right? So this is saying there's a line at this orientation, okay? If you want this next orientation, you do a similar thing, but for a slightly different pattern of connections, right? So now you unroll that all across the brain. What if you want to do a curve? Well, imagine a curve of something like this. So you have neurons that recognize each of these pieces. The next layer down, you connect those together such that you recognize this shape of curve at this position. You want to do different shapes of curves. You have those connections lined up. You want to do a different position and so forth. I'm not sure how motion plays into exactly where that happens in the visual cortex, but you can use time delay, right, to say, well, I saw a line here at time t, and I saw a line here at time t plus delta, so I think that's one line that's moving. Okay. At some point, this structure breaks down, and when you get to much more complicated objects, right, the structure is a little less clean. But as for low-level vision, it's incredibly parallel and really pretty elegant. Okay, so at this point, we're way past what I know about neuroscience, so I'm going to stop right there. But those two books should keep you happy for a while if you want to learn more about this stuff.
Question?
Please comment on the possibility of combining the spiky model with the knowledge.
Well, so the question is, how would you combine a spiky model with this? I don't know that it makes sense to combine them, at least not in the same layer, right? You could imagine a machine that used maybe spiking at one level and convolution at another level, detail. But yeah, I mean that's a very algorithmic question, right? The hardware is very different, right? So there's probably no hardware benefit from combining them. Whether there's an algorithmic benefit to using one model in certain parts of the recognition process, I don't know. But there's probably doesn't make much sense at all from the hardware perspective.
People figure out how to take proper techniques.
I don't know. Hopefully we'll hear about that later on this week, but I don't know. Okay.
I think before we end it, our step so kind presenting with the souvenir. This is the set of cosmetics.
Oh, great. Thank you very much. Thank you.
Now we play.
Oh, good. Okay.
Okay, 谢谢。